welcome for this webinar addressing advanced air monitoring for hazardous environment in case of accident, in case of emergency. For this webinar, we will have several speakers. Three speakers, Major General Petr Ošlejšek from the Czech Fire Service and the Federation of the European Fire Officers, FEU. We will have also a presentation by Théo Habrant-Claude from INERIS, who will bring the research perspective, the good practice perspective after the presentation of Petr Ošlejšek, which will be on the perspective from the end user, from the practitioner, from the firefighters. And finally, we will have the presentation by Nelson Fernandes from PhotonSense Tech, a company developing some innovative solution for the monitoring of a hazardous substance in the atmosphere during a catastrophe, but not only during a catastrophe. So this is the agenda. As usual, we have the three moments with the responder setting the scene, explaining what are the needs from the emergency responders. We will have the presentation about the good practice regarding the measurement of hazardous substance in the atmosphere by Théo, and the presentation of innovative technology. And by the way, PhotonSense has been awarded by the DIREKTION project during a ceremony last June in Greece. And after these three presentations, we will have a moment to exchange, to discuss with the speakers and answer your question. This webinar is being organized by the DIREKTION project, but also with the support and cooperation of the Disaster Resilience Society Stakeholder Hub. This DRS hub is operated by CMINE, and this is an interesting initiative that concentrates in one place knowledge and tools that are useful for those who are interested by disaster resilient society topics. We have a place here also with this hub to connect with other colleagues interested by the same topics, and we store all webinars, all communication on this topic on this website that you can find using the QR code on the top right of your screen. A few words on the DIREKTION project that I coordinate. So my name is Olivier SALVI, and I am President of INERIS Development and also coordinator of DIREKTION project. The project started in October 2023 to promote innovation, to facilitate technology uptake, and enhance the cooperation between different groups of stakeholders to improve the use of innovative technology in the DRS domain. So the project is a network where we promote existing knowledge and try to disseminate about good practice in all the community, and trying to reach also new audience. We also try to understand what are the future needs, current and future needs of emergency responder, to see if there are technology, if there are solutions already available, and share with them. And if these needs are not satisfied, we try to create the environment so that we have the ingredient for co-development of innovative solution. So in a nutshell, this is the objective of the project, and you can read our mission on the right. So we try to energize the community to develop, to enable the use of more innovation. I will start right now by giving the floor to Major General Petr Ošlejšek from the Czech Republic Fire Service. So Petr, you can turn on your camera and start your presentation. The floor is yours.
Okay, thank you. Just the control. Do you hear me?
Yes, we can hear you very well.
Okay, thank you. Thank you for the possibility to present our experience from the first responder point of view. Just a short introduction of myself. Just a moment, because okay. I have more than 26 years involved in fire rescue service of the Czech Republic, and I passed different positions from the local to the national level, and from the operational to the strategic level. And now I am Deputy General Director of Fire Rescue Service of the Czech Republic. I am also involved in some other organization and activities. Very shortly, Czech Association of Fire Officer is a non-governmental organization who cover fire officer of the Czech Republic, and our aim is promote fire prevention and resilience of the fire service and the citizens in the Czech Republic. And the very similar organization as the Czech Association is the Federation of European Fire Officers, which is the European one organization, which covers almost all representatives from EU countries. And we try to increase the safety and security of the European citizens and resilience of citizens, and of course, the resilience of the first responder. And we try to share the best practice, and sometimes we try to push to the European bodies to promote civil protection or fire brigade activities. I will continue with the operational reality. Many of you are involved in first responders, and what is a typical when we arrive on the scene is the lack of information. For the good setup of the incident command system, we know about the threats, about the situation awareness, and the right time for the right incident command system is necessary for the success of the rescue operation. If you look to this nice picture, tomorrow it will be 1 year anniversary of this accident which happened in the Czech Republic. It was a train who carried out almost 1,000 tons of benzol, which is the flammable and very toxic liquid. There was a train accident, and due to destroying of the tanks, the benzol go out and start to burn, and probably it was one of the biggest disaster with the benzol outside the chemical factory. When we arrived on the scene, we just recognized the first signs. It means smoke, fires, and the heat. And after that, we set up the system for the air monitoring, for the monitoring of the contamination. And this emergency was a typical large emergency when we need to set up the system for the air monitoring and for the continuous evaluation of the situation awareness. Generally, what is a typical when we arrive on the scene, sometimes we don't have enough information about the threats, about the situation, but we need to start very quickly with the decisions and with the rescue operations. Sometimes we need to decide if we start the rescue or if we protect our crew. Sometimes we need to combine this decision. What is also important that the situation can change very quickly. It depends on many factors. It's connected to the substances. It's connected to the weather and other conditions on the emergency side. And as I said before, early decision affect the safety. If we don't provide a quick decision, we can create unsafe condition for our crew. Air monitoring, it's important in all phases when we look to the disaster management cycle. If I start with the preparation, it's very important to know how it's look with the normal air condition, how it's look with the presence of the different chemical substances before the emergency start. The monitoring, the continuous monitoring of some substances is necessary for right decision when we speak about the early warning or when we speak about the protection of the population who lives around some sources of the risks. If you go to the response, or if you go to the preparation phase, it means we need to have a system how to very quickly use different detection devices and how we can transform the data from the devices to the information which is necessary for the decision making. If you look to the response phase, there is also very important to really start with the monitoring of the air on the site of emergency, because based on that we are able to provide some identification of the risk. First can be the qualitative identification, and on the second it can be also the quantitative identification of the risk, and based on that we are able to set up the zones and we are able to use the adequate personal protective equipment. When we go to the last part of the response and to the recovery, the continuous monitoring of air support us for the evaluation if it's our activities on site, if they're going to the right way, or if we need to make some changes in our decision or in our tactics. And the last phase, the recovery, is also important to provide some measure of the air, because it can confirm if the situation is safe or if our activities went to the final safe situation. What is a typical for hazard environments when we speak about the gases? Some of the risk we are able to see directly when we came on the scene. We can see the smoke, we can see the flames, we can feel the environment, but many of toxic gases are not visible, and the impact of the toxicity can be not in a short time. It means it can not be just the acute impact, but there can be some lapse time when the negative came to the citizens or to the environment. It can be not just about the toxic gases. What is also important when we came on the scene is a measure of the oxygen, because sometimes it's too low level of the oxygen, sometimes it's high, which can generate other risk connecting to the explosion or to the specific burning of different materials. It's very important to provide the continuous air measure on the different places, because we need to have a common operational picture how it's look with the environment on the emergency. And especially when we speak about the gases, it's sometimes very, very difficult to find a way how to provide this continuous measures, because gases are very connected to the meteorological situation. It's connected to the wind, to the buildings, to the temperature, and many other aspects. How we use the information, what kind of information we need to know for the fast decision cycle, because on the beginning we can use just the small pieces of information, and we need to make a decision about the small pieces of information. And when the situation is evaluated, and when we parallelly set up the system for the measure, we need to make some correction or some changes. targeting of rescue operation. Incident commander need to know what happened on the scene, what is necessary for the success of the rescue operation, and what is necessary for the protecting of the crew. He need to know just not to think what's happened direct on the scene, but he need to think how can be the development of the situation. It means some toxic gases or toxic clouds can move to the area, which can be 100 meters or kilometers far from the emergency. And he need to provide some early warning and provide the instruction to the population who can be affected. And very important is also to provide this continuous reassessment, because as I said, the situation can change very quickly. What is also important to divide is the data versus information, because you can see on that devices you can see just the numbers, but you need to transform the numbers to the information which is necessary for the right decision. It means it's not just enough. This is concentration in volume percentage, or this is the concentration in ppm. You need to know what it means. It means if it's safe or if it's the unsafe, and based on that you need to make some changes in a decision cycle. Sometimes the sensor, because it's the technical devices which is based on some electrochemical or chemical reactions, can lie. It means they can be some cross sensitivity. It means the sensor can provide the information which are not connected to the real state. It means it's very important to think if I receive this information about the concentration of that gas, if it's possible that this gas is on the emergency scene. It can be the typical for the gases from flammable gases and from the technology which use the measure of the heat in the sensors. They can sometimes provide the wrong information, or they can sometimes lie. And it's very important to look on the air monitoring in the context, because sometimes the context and evaluation of the situation can be important than measure in one place. This is what we can say from the sensor to the situation awareness, because the situation awareness is very important for a right decision, and the situation awareness can change very quickly. It's also very important that all first responder on the scene be informed about the situation. It means it's not enough just to share with them the data, but it's very important that all first responder understand what this means, especially when it's a different in the situation when it's a different agencies on the emergency side, like a police, medical service, and the firefighter. It's very important to share not just the data, but also the information, and verify if they understand what is the real danger or real threats on the emergency side. As I said before, the measuring of the air, or measuring of the qualitative or quantitative parameters is sometimes very difficult, because the gases can move. There can be some some clouds with a high concentration, some clouds with a low concentration, and according to the meteorological condition or according to the flow around the buildings, it can change very quickly. It means we can have some exact data from one place in a specific time, but after 2 minutes, can the situation change very rapidly. It depends especially on the gases. Some of them they go up. Some of them flow like liquids. What is very important is set up in the right time, the right monitoring strategy, and it's important to think what kind of gases or what kind of threats we expect on this emergency, because sometimes can be the toxic, sometimes can be the explosive hazards, sometimes there can be gases, sometimes can be aerosol or a different phase of the matter in the air. Sometimes can be the short-term impacts. In some emergencies can be faced some long-term impacts of the expedition. The specific condition can be in a case of the radiological or nuclear parts, which can be also in the air. And wrong assumptions lead to poor sensor placement and unsafe zones. Dispersion and prediction. Sometimes we can use the models which can support us, but it's very important to provide a real measurement, and because the models used from mathematical modeling and the real condition can be very different, but models can also support commander on the scene in decision-making process. Operational sensing tools. It's very important not just to have the right high-tech technology, but we need to know use it in the right time on the right places. Sometimes we use the portable multi-gas detectors. It means the operators use it in the hands, or he has the detector on the PPA and continuously provide the detection. And if the concentration go over the limit, the detector inform them that he is in a specific danger zone. Sometimes we use the remote sensing. It means we are able with FTI Air or CGIC devices provide the remote sensing of the clouds with the toxic or specific gases. Sometimes the situation is dangerous, then we need to use the robots which we can send there with the measure devices. Sometimes we use the drones for the mapping of the clouds. Then sometimes we provide some samplings for later laboratory test or later laboratory verification of the environment. And it's important for each measurement, for each situation, use the right tool, because the right tool, right information can reduce the risk on the operational side. I just, for example, prepared 3 scenarios. One scenario when we can use the air measure devices is industrial facility. It means in industrial facility in the production site or in the storages for chemical substances. There is a permanent measure. There is a permanent detection. It means if there is some leakage of the gas, the system can not just warn the employees on the side, but he is able also provide some other action. It means like a closing of the valves, some starting some sprinklers which can reduce the spreading of the gases, or provide some other activities for the prevention of the secondary effect of the emergency. The second example is for the early warning of the citizens, especially when the industrial facility is close to the occupied area. It means there can be some sensor who can be installed in the emergency planning zones. The sensors communicate each to other and provide a continuous measure. If there is some emergency with the leakage of the gas, they can very quickly inform the population or first responder, and they are able to provide the citizens the right information in right time, and protect them against the threats connected to the industrial site. And the last is active response measurement. It means it's a measurement which is provided directly on the scene. It's very important to use it for the zoning of the site, to the hot, warm, or cold zones. It's necessary to use the information from the measured devices for the choosing of the right PPA for the measure of the exposure of the people, of the rescuer. Is necessary also for the checking of the quality of decontamination. And it's one of the most important which need to be provided on each emergency. And just on the end, why air monitoring exists. Air monitoring supports decision in uncertainty, but it does not remove uncertainty. It means air monitoring can support the commander on the scene, can support to achieve success of the rescue operation, but for that need to be used right devices, right in the right time, in the right condition, and they need to be the system how to transfer the data from the devices to the information and to the support of the decision-making process. It was my look to the air monitoring from first responder or firefighter point of view, and thank you for your attention.
Thank you very much, Petr, Ošlejšek. It was very useful to understand that knowing what are the pollutants in the air is very important to know what to do, during the event, to remove uncertainty and select the best device, best tool for the emergency responder. But also what was interesting to see is that it's to prepare the future, to prepare what will happen after the incident, and to know also how to deal with potential pollution and so on. So thank you very much. Bastien is working to enable receiving questions, but let's move to the next presentation, and I invite Théo to take over the presentation and move to the next slide to present the perspective from a research organization. Did you manage to take the control and move to the next slide?
I think so. Yeah, I would like to move. Okay.
Yes, so please tell us about what are the good practice regarding monitoring of air quality or air pollution during an event, and also what are the strategy to do a real good quality measurement.
Okay, thank you, Olivier. So good morning and maybe already good afternoon for some of you. I am Théo Habrant-Claude, and I'm really glad to share what we have defined at INERIS as guidelines for air monitoring in emergency situations. I will just share you a presentation primarily intended for environmental stakeholders, but even if you are not, you can, I think, learn a thing or two, and you will see that it is very much in line with the previous presentation. So to give you a piece of context, I will mainly focus on industrial fires, and I took the example of the one of Lubrizol factory and Normandie Logistique, which occurred in 2019 in Rouen, in France. And the feedback of this huge fire was that it was crucial to rapidly deploy public resources to make accurate sampling and also to make accurate measurements. So the French Ministry of Ecology asked INERIS to propose a response, and our general idea was to adopt an accurate and sparing approach in order to make every sample count, and especially to minimize the risk for the people who carrying out the measurements and the sample, and especially for firefighters. So in this presentation, I will focus mainly on the first two stages of fire, which are emergency phase and immediate follow-up phase. The first one is when the firefighters are still fighting the events. And the second one is when the event is under control, but there is still emission in air. And I will focus, obviously, in this matrix of emission. I will not tackle the post-accident phases because of a lack of time, but you feel free to ask questions if you want. So the response proposed by INERIS was composed of 3 tiers. The first one is a kit for sampling and direct measurement. You can deploy easily on site. I will describe it in details later. And the second one is a mobile laboratory. And the third one is a mobile measuring platform. And I will share you a glimpse at the end of my presentation of these two tiers. So I will run through the strategy for sampling and measurements. And to define a proper strategy, you need to ask some simple questions, which are, so the first one is obviously what is burning, and underline which compounds are emitted. So sometimes that's already pretty much known as the event in the Czech event with benzene, for instance. But you have often doubts on what compounds are emitted. So that's really crucial to well define the chemical fingerprint in the plume. And of course, you can also ask if that's large-scale events, and that will define the complexity of the events. If you are more in fact, the context of the site, you need also to ask if there is a firefighting water basin before. If there is none, that could become a high priority to sample the firefighting water because before it disappears in the environment. You need to ask also which areas are affected by the atmospheric fallout, which is very linked to the meteorological condition and the plume dispersions, to know the hotspots in which you might have to sample the emission, the pollution in the air. And the last one is also what was the pollution level before the accidents. And that point is really that point matters a lot also because otherwise you cannot assess precisely the impact of the accident. And everything is linked, of course, with exposure. So you have to define also the routes of exposure in this context. For instance, direct exposure through air, and indirect exposure through integrative matrices, such as groundwater, livestock farming, or crops. To sum up it works for exposure, every mechanism, you can look at this schematic. And first of all, you have something burning here, which emit gases and particles, which dilute in a plume. And that entails directly exposure through inhalation. But you have also atmospheric fallouts, gases, particles, and deposits, which can contaminate surface water, soil, vegetations. And don't forget that you have also your firefighting water, which can also contaminate by spillage or infiltration different matrices, for instance, groundwater. And everything can expose also people through ingestion. So we will focus here in this presentation, but yeah, there is also a lot of work to do with other matrices, as you can think. So for the first tier, that composed of cases of equipment with sensors for real-time analysis on the field, and also sampling equipments, and they are talking to each other. You can carrying out some qualitative or even semi-quantitative measurements, and that provide additional information on the sampling point. And both are crucial because you can, thanks to these informations, optimize the analysis strategy. Always keeping in mind that you want to make every sample count and to have the best analysis possible in the lab, or in our case, in the second and third tiers, with low detection limits. So that's a lot of equipment. So I will not describe everything, but I will focus on air sampling and also give you a glimpse of which equipment we are using. So I will just move on how you can use that on the field. And the main strategy for air sampling is to choose the right container, the right sampling location, and also the right duration to sample. So the first thing to do is to target the chemical fingerprints with a brief sample, because the concentration is often quite high, and you don't want to have the people carrying out the measurement, the sample, bearing more risks. So a short, brief sample is enough. However, for inhalation exposure, you have to compare with the reference values, and you have to be in the context of what we call the very brief acute exposure. So you have to make a longer sample, or more than an hour and less than 8 to do so. This sample is always coming with a background sample to have a comparison value, to know the level of pollution before the accident, and you can do that upwind, a bit far from the events, but still local. And to sample gases, you can use a canister, for instance, which is very good because you can keep your sample for 7 days for volatile organic compounds, and that's a very good sample to give to the lab. However, that's quite expensive, and that's also costly to clean. So you can make some complementary samples thanks to bags and a sampling case, which is vacuuming the gas around the bag to make it inflate. And that's useful because thanks to that, you can get rid of a pump before the bag, because once you are taking a dirty sample, for instance, directly in the plume, your pump is dirty and you can contaminate the next sample. And you can analyze this bag 1 day after for volatile organic compounds, until 1 day after. And if you are quick enough, you can also get some information on mineral acids before they are condensing, and it disappears. It disappears in the moisture in the bag, and you can measure directly some things on the field. So I will just present you quickly what you can do. Obviously, we have, as also presented in the previous presentation, some safety sensors, but we have also some sensors for to monitor combustion tracers, such as particulate matter, soot. By soot here, I mean black carbon in air, and volatile organic compounds. We have also some high-level equipments to identify families and even specific compounds, and sometimes semi-quantify them, targeting volatile organic compounds or compounds containing sulfur, phosphorus, or even mineral acids. And that's really useful to optimize analysis strategies, and that's crucial information to provide to the lab afterwards. So if you have any changes in the weather or burning materials, for instance, you have tires burning and afterwards some lithium-ion batteries, you need to make another round of samples to characterize the chemical fingerprints, to assess people exposure, and then sometimes you have also to take again your pollution background. Finally, I will run through the last two tiers. So the first one is a laboratory track. I will not go into many details because that is quite complex, but it has quite a huge autonomy with a power generator on site until 7 days. And inside you can find, beyond other things, two automated thermodesorption gas chromatography coupled to mass spectrometer. They are identical on both sides, and you can, thanks to that, deal with a lot of samples, especially canisters. And they can target especially volatile organic compounds. But we have a calibration gas bottle for 45 VOCs, potentially emitted during a fire, an industrial fire, and for which we have toxicological reference values. So that's quite optimized for industrial fires, especially large-scale ones. And finally, the third tier, it is a mobile measuring platform. It has also some autonomy, but only with lithium-ion batteries. And you can see little horns on it that those are sampling probes to sample particulate matter in a way as representative as possible of what you have in the plume. And it is equipped also with a data acquisition station, which can provide a feedback in the cockpit and also online access for concentration cartography. It is intended to talk with the first tier. You can find some high-level equipment almost equivalent to what you have in the first tier for soot, for particulate matter, and a very high-level equipment for a lot of volatile organic compounds. You can find also some equipment for heavy metals, and that provides a big picture for hotspots for atmospheric fallouts, and also, as said in the previous presentation, that can provide measurements on the field to give modeling, to give inputs to models, and to have a nice forecast of the plume, of the impact of the accident. Finally, I will conclude by reminding you the global approach. By first, you need to deal with samples in air matrix, because that's usually what it is disappearing first. with brief samples for chemical fingerprints and longer samples for to assess population exposure, and also coming with a sample of the pollution backgrounds for comparison values. After that, you can tackle other matrices such as soot, and by soot here I mean surface deposits, firefighting water, and polluted soils, which comes from also with a reference, always to have a comparison value to assess with accuracy the impact of the accidents. And after that, you can deal with integrative matrices such as groundwater, eggs, etc. Of course, there are some exceptions, but I will not enter into detail here. And if you have any changes in weather or burning materials, please do another round of sampling of the chemical fingerprints, and especially of the population exposure. And provide every information you have to the lab so they can make every sample count and have lower detection limits and give you a nice feedback of the compounds and the concentrations. So we will publish guidelines about that in a while, I hope. So that's it. Thank you for your attention. Sorry.
Thank you very much, Théo. It has been very, very informative to see that there are many different types of devices to make the sampling, to collect data on the pollution. And also, I was interested by the strategy that it's not enough to have the device, but you need to have some strategy to know what to do with the data that you will acquire thanks to the measurement. So I think we can come back to this topic later during the question and answer part. And now I would like to invite Nelson to take the control and describe or present us the technology that you are developing, Nelson. Turn your microphone on, please. You are still on mute.
Yep. Thank you for having me on. And yep, I mean, we've heard quite a lot about the scenarios. I would like to take you back and walk you through some of these scenarios. Imagine an industrial facility or a military base or transport hub. An invisible release occurs, or one with full fire blazing and the smoke blazing out in one of these places. There's no explosion, there's no alarms, just air. In most cases, detection happens only after exposure, when someone feels symptoms, and that delay defines the damage. OHM was built to change that equation. We don't wait for air to enter a sensor. We interrogate the atmosphere remotely and continuously. This is not air monitoring. It is real-time atmospheric intelligence, a game changer. That was my first slide, sorry. Today's systems are largely reactive. As you've seen already, they measure at a point, and they depend on air being pulled into the chamber, and then they're taken into the lab for analysis. Gas plumes are dynamic. They shift with wind, temperature, and urban geometry. So we have a structural mismatch here right now. Dynamic threat and static detection. That mismatch creates operational uncertainty. And this gap exists in both military installations and civilian environments. As you've already seen, air behaves like fluid physics. The plumes expand, fragment, and redirect in minutes. A single reading will tell you what happened in that one place at that moment in time. It does not tell you where the threat is moving next. In both deliberate CBRN events or industrial accidents, response speed must match the plume speed. from what we've seen so far. And if detection lags movement, exposure will increase. OHM operates differently. We illuminate the air column with a laser. We analyze that backscattered light in real time. No pumps, no consumables, no physical sampling in the hot zone. It is standoff. It is continuous. It allows monitoring from outside the risk parameter. That fundamentally changes responder safety. Every gas molecule interacts with light in a specific way. Those interactions form spectral fingerprints. OHM uses a single laser source to illuminate a defined air volume. The backscattered light carries encoded molecular signatures. It extracts both what is present, how much is present, and machine learning separates the signal from environmental noise. It is physics enhanced by intelligent analytics delivered in real time. Operationally, this translates into 4 critical advantages. First is early warning before symptoms appear. Second, dynamic control of hot and warm zones. Third, reduced responder exposure through standoff positioning, and that is the most important one as well. And fourth, lower life cycle cost compared to consumable-based systems. This is decision cycle compression. Faster clarity means safer action. OHM is not limited to fixed installations. It can be integrated onto moving platforms, including drones, vehicles, maritime assets. This enables mobile atmospheric intelligence during operations, border patrol, disaster response, or industrial inspection. Mobility expands the coverage and allows monitoring where the risk is evolving in real time. The capability moves with the mission. I would like to walk you through some more scenarios. Imagine a military installation. Minute 0, there's been an unknown release. And in minute 3, the spectral anomaly has been detected remotely. Minute 5, your command receives confirmation. Minute 10, your parameter has been adjusted, your personnel redirected. No exposure. This shift force protection from reactive response to preventive, proactive control. Now consider a forest fire or an industrial toxic release near a city. Without clarity, response often over-evacuates. With real-time plume tracking, you define the concentration gradients, ppb, ppm, and what gases you want to see, right? You adjust the evacuation zones dynamically. You communicate based on data. Public confidence will increase when decisions are evidence-based. Radioactive materials like cesium-137 and iodine-131 are used in hospitals, industry, and nuclear facilities. The problem is when infrastructure gets old or maintenance fails, leaks don't always show up right away. You often only discover them after contamination has already occurred. Sites that store this nuclear waste need constant monitoring, not just inspection every few months. Early detection is the difference between a manageable issue and long-term damage. This is about protecting people, protecting the environment, and making sure small problems don't become permanent ones. OHM has validated system performance in relevant environments. Our next step focus on operational qualification and scalable manufacturing. The next step is TRL9, operational pilot deployments with defense and civil partners. Hybrid threats are increasing. CBRN risk is evolving. Urban density amplifies consequence, and speed defines strategic advantage. Detection after exposure is no longer acceptable. Atmospheric intelligence must become part of security infrastructure. The capability exists. The question is deployment timing. OHM is designed as a true dual-use capability. The same platform supports defense force protection and civil emergency response. This strengthens resilience across military installations, critical infrastructure, and urban environments. Atmospheric intelligence is becoming strategic infrastructure, and strategic infrastructure must be trusted, scalable, and aligned with Europe's long-term security objectives. For those interested in technical depth, we apply high-resolution optical spectroscopy combined with elastic scattering principle. Machine learning separates molecular signatures from environmental and variability. Our calibration supports multi-gas detection at the same time and scalable expansion. The architecture integrates across fixed and mobile platforms. The system is modular, adaptable, and deployment ready. I will walk you through a small video of our instrument because I couldn't do an actual demo. So here's a quick demo showing you the device. So that's what it is. We can combine, we can make this device smaller. There you see we spray some aerosol and we get the reading instantly on our dashboard. You can see all the different gases we have at the moment. If a particular gas is not on that list, we can bring it, we can calibrate the equipment to detect those gases as well. So there's smoke in the air, detects it, and you can see it rise. So that's it for me. Any questions? I'm happy to take that on board.
Thank you very much, Nelson, for showing us the capability of OHM system and the range of operation, and also how it works in concrete with this example on the video. So there is a question from one participant, Enrique Keitzer. What are the difference and similarity between your system and systems such as SIGIS and Hi-90? If you know this system, I don't know.
No, I don't know. So quick thing is our system is real-time, it is portable, it's ready, and it's integrated with any other systems because we have an API that can integrate and talk to current any other systems in there. And you could have it on a mobile device as well.
And do you
that kind of...
Sorry, do you see some complementarities with the technology and the device and the strategy presented by Théo? Some complementarity of OHM system compared to the usual, I would say, techniques, even if it is very sophisticated sophisticated. Your device seems to be for multi-component with real-time monitoring, portable. So do you feel it can replace, or it is complementary? So this
will replace, I would say, more than anything, because you have no consumables. There are no consumables. You don't need to take it to the lab. The laser shoots out and it gives you the reading of that gas. And as the plumes are moving, you can have the laser moving in a 360 degree, and it'll give you latitude, longitude of where that gas is as well, and at what volume, at concentration levels. So it's complete real time.
Yeah, I would like to hear also the reaction of Théo about your device.
Yeah, thank you, Olivier. I would like to add just to clarify things for the previous question. I know the Sigis and the I-90, that's Bruker equipment, and they are FTIR using the light of the fire. So there are some firefighters in Hamburg using them. So maybe, Nelson, you can use this information to clarify things. And just to say something to answer what you said on the replacement of equipment, that's remote sensing is really useful in this case, because you minimize the risk for stakeholders. However, taking samples matters a lot, and you cannot compare a measurement such as remote sensing as you do with toxicological values. For that, you need a sample because with the remote sensing, you only have a concentration over a lens, and that's not linked to what people experience for exposure. So that's really nice for acute exposure and for firefighters, and to define a perimeter, but you cannot use it as to assess the impact of the fire. You can use it to manage the fire during the crisis.
Well, not just fire, because I mean we can do all other gases as well.
Yeah, sorry,
right?
So that was my example.
Sorry,
that can be a release also.
Yeah, so we could do it in ppm or ppb as well.
Yeah.
And it's all in real time, because I mean, when you take a sample, you're taking a sample of that gas at that moment in time, at that spot.
Yeah.
So that's the biggest difference, and depends on how you take the laser into the environment. So if you put it on a drone and you move it around closer, you're getting more readings. And you know, if the drone, the gimbal is rotating at 360, we're giving you a much more accurate reading.
Yeah, that's a very nice information, especially to use it as an input for modeling, for instance, as our third tier. But once again, you cannot use that to assess people exposure and to compare it with toxicological values.
Okay.
That's just this part you cannot do. For the rest, I agree.
Yeah.
But yeah, so it brings some immediate information for firefighter, and I would like to invite Petr to open his camera and also participate in the discussion. You raise your hand, Petr, if you are available.
Yeah, I am. Okay,
yes,
thank you. Thank you for presentation of this new technology, because we have experience with Sigis. Now we are in the process of the purchasing HI-90, and we will be comparing. But sometimes there are some limitation due to like a normal weather condition. It means if it's like the cloudy, like a moisture, or something like a small aerosol inside. Do you have some experience how it's react your system on this disturbances in normal atmosphere?
We should still be able to read it. We're happy to come down and collaborate with you guys and show you the equipment working in real time.
Yeah. Okay. Thank you. But
very good. So I think it's interesting. Yes, Théo, and we have also a question in the chat that I will take just after.
Okay, so that was really a short question then. That's for Nelson again. Have you tried your equipment in a simulation of complex fire, such as a platform like we have with INERIS? For instance, we can burn complex things in a big room in which you can place your equipment outside and monitor what is inside. And we have also a huge monitoring of the plume, so you can compare your data.
That would be awesome.
That?
Yeah,
Okay.
absolutely. we would be more than happy to work with you guys on that. Yeah, and do the comparisons. Yep.
Okay,
and that's exactly what we're looking at to get TRL 9. So, you know, we're all there. We're ready. All we need is an uptake of the technology.
Yeah, and
as you can see, it's a game changer.
Yeah, and I think it's important to have this kind of demo and to test it in real, to really appreciate the functionality. And as you said, if you manage to use this new technology with a laser, it opens a new area of measuring and having quick information. But I understand that there is some interest to test it in real and appreciate the quality of the result and compare with other techniques which are already proven. I think this is the main point, that it's important to compare with existing techniques and see that it is consistent and measure the advantages. We have a question to you, which has been posed by Paul Thomas from Biox Hale. Nelson, are you able to comment on the effect of altitude on the calibration of your system? Paul says, I'm interested in the interaction of changes in pressure across the laser path length. I appreciate that it is a technical challenge. So any comments on the impact of the altitude and the pressure on your measurements?
So far, I mean, with the drone, we've taken it up to 200 meters and we've had no problems. So it just depends how higher you want to go, so we can calibrate the equipment for that. So it all depends on the scenario. Like we're talking to ESA at the moment for use in space. So that's a completely different ballgame. So we're looking at that and how to calibrate, and we're working on that at the moment.
Okay, so for the moment, you do not have a clear answer, but you're working on this.
Yeah, exactly, because it depends on the requirement from the customer. As I said, we are now looking for uptake, so it depends on what the customer wants. We're happy to work and test that out on that scenarios that they want, very specific.
Okay. Thank you very much. So I would like to, I have seen Marek Gottfried raising his hand. Maybe you can put a question in the conversation, in the chat, so that we can take your question. I would like to ask Théo if you know if there are some similar trucks like the one you presented for the second tier and the third tier during your presentation. Do you know if there are similar trucks, I don't know, in Czech Republic, in Italy, in Spain or in Finland?
Yeah, in fact, that's not my favorite tier, because that's another team at INERIS dealing with it. But I know that in Belgium, they have some. And there are also some equipment in France dedicated to nuclear contamination, quite similar, not with the equipment inside, but with the conception of the truck.
So measuring different things, radiological substance and yeah. Okay. Petr, you want to add something?
Yeah. In the Czech Republic, we have a similar system, because some years ago, it's more than 25 years ago, we adopted our structure like the former civil protection. It means the civil protection in the Czech has had a laboratory around the Czech Republic, and since 2000, it's the laboratory system, the part of the Czech Republic. It means we use 3 or 4 level. The first level is like a basic detection. The second level is advanced detection. It means it provides some special predetermined fire brigades. And on the third level, we have the laboratories, and they have a possibility to go out on the scene. They provide some basic measure, and they are able to provide also some small laboratory tests directly on the scene. But in the third level, they have like a special chemistry laboratory. And we very often use it in the case of the large fire, or when we need to provide like a more deep analysis when we speak about the air, or when we speak about the soil or water. And just if I ask to Théo, how it's look with the protection of the staff who is operate with this car? It means there can be some chance that they will be affected directly by the cloud or by the chemical issues. Do you have some special ventilation system in that car, or some special PPA?
There are some well-defined protocol to get samples and to keep it well ventilated and to not expose people inside. But the truck is meant to be close to the site, but not so close. Just to bring it close enough to manage samples, but to keep people out. And also for the first tier, in fact, we always need the help of firefighters, especially to take samples in the plume. Because we don't want to intervene directly, because that's not in the logic of the action there. But we can help to teach firefighters how to sample directly on the field, and we can keep our team far enough to minimize the exposure, but we still have some gas mask to protect ourselves.
Okay. Thank you. It's very interesting. And there is another question coming from Marek Gottfried in the chat that Bastien has relayed. It's about how it works when you are dealing with substance you don't know. So how the responder will use the device if you don't know at all what is inside the smoke or nearby the smoke. So this is a question. So maybe it's a question for both of you, for Nelson and for Théo. So you want to know how does it look like for responders that are responding to unknown substance to use your device? Because in one situation with the AUM system, you may have some remote measurement and instantaneous information, and with the sampling, it means that you need to go on site and start making some measurement, Théo. So and in between, sometimes the fire develop, and the responders, they have to work or to do their job.
For my part, that's really about the chemical fingerprints, because in fact, when you know the pollutant emitted, you don't need to make samples for the chemical fingerprints, but we have always doubts about that, and sometimes you don't even know what is burning exactly. So we have some identification equipment to do that, and we had a study of which pollutants can be emitted during a fire. So we target precise compounds such as compounds containing sulfur, phosphorus, mineral acids, and we have also a mass spectrometer, a portable mass spectrometer, to identify volatile organic compounds and even semi-quantify them. And that's for on-site equipment. For the rest, we have also a lot of equipment in the lab, of course. But in the third tier, we can deal with heavy metals, especially traces in particulate matter. So that's dealing with a nice picture of everything that can be emitted there, except for difficult substances such as dioxins or hydrocarbons, polycyclic aromatic hydrocarbons, and you can deal with that by sampling, especially visible soot.
I see.
Yeah. So for us, it's pretty straightforward because we've calibrated the equipment already for 20 gases, and all the VOCs are in there already, so we can detect all of that straight away. And if needed by the customer, if there's something else that's not there, we can actually look at that signature and we can say, hey, there's some other gases in there. Yep, we have not calibrated it, so we won't know what that is. But for the gases that we have calibrated, we can tell you straight up in real time.
And I imagine that you can include, after many operation intervention, you can include additional gases and enrich the database, which is supporting the interpretation of the measurement of your device.
Exactly. So for biohazards, chemicals, or even nuclear things, all we need to do is calibrate it. So if we get the biohazard, the biochemical or whatever, we could actually put it into a tube and pass it through. It looks like this. It's slightly different. It just has a pipe coming out here, and we put the gas and the laser. So it's all not contaminated as such. So the laser, we pass it through the laser. We look at that signature for that particular gas, and we calibrate the equipment based on that. So it takes us about a week or 2 weeks to get that done. So if there's any new gases or whatever, it's easy for us to do and add that up. So
Excellent.
we're talking to TNO to get CBRN stuff, some nuclear and stuff. So that's where we can then calibrate the equipment.
Okay. Petr, and then I will take the question from Ari Stefanov, which has been posted in the Q&A. So Pet, please.
Yeah. Thank you. Just a Nelson question to you, because I remember when we start using the Raman spectrometry, which is based on the laser which emitted some special Raman spectrum and combined it with the library inside the devices. Sometimes we think about the danger of initiation of the explosion of the burning by the laser stream. Probably do you use some low energy laser for that? It means there is no danger of starting of initiation of the explosion in your devices.
No, so it's a very low range. Basically, the laser operates from 5 meters to 5 kilometers. So it just depends on the strength of the laser, but it is all safe.
Mm-hmm.
As far as so we've tested it. We've got some ISO certification testing basically, and we are quite confident of that. So
interesting. Okay, so I have also a question. So as I said, from Ari Stefanov, the question is to Petr. Where is the cutoff line that you draw in which you do not perform air monitoring? So the question is, for a fire in an apartment, you will not do the air monitoring. When do you start using or deploying this kind of device to control the air quality in fire with benzol, as you mentioned in your initial example, for example? So when do you start? How many devices do you have in each station, or only a CBRN team in Czech Republic? So can you tell us about your strategy when you use this kind of techniques?
Okay, thank you for this question. As I said before, in the Czech Republic, we have generally two levels of the hazmat predetermination and special laboratory level. On each fire truck in the Czech Republic, we have the basic detection for the explosion and also for like a basic chemical substances like ammonium, chlorine, and some specific. On the level 2, we have other special devices which based on the colorimetric principle of the detection. And we have also some specific devices, as I said, Raman, GDA, and other specific devices. And on the laboratory stage, we have like a mobile detection trucks, which are able to move around the incident. And it's connected to the response times. It means the average response time in the Czech Republic is 15-20 minutes. It depends on the far from the fire station. And on each scene, we are able to start the basic measure when we speak about the explosion. And we also may provide a measure of the radiation. And if we accept some special gases, we can use these basic devices. And when we speak about the response time for the laboratories, is up to 1 hour or 90 minutes from the call. And we are able to collect the laboratories on one place. And if I go back to the emergency with the train, it means that the first laboratory came on the scene after 1 hour. But due to large situation, we invite other laboratories which came there plus 2, 3, 4 hours. And what was interesting in that case, it was the first time when we used this sniffer on the drones. We cooperate with the colleagues from the Slovak Fire Rescue Service, and they deployed there these drones with the sniffer. It means we are able to measure the air quality in the different height and the different distances. And it was also first time when we use the robots for the measure of the quality. It means the robot in that case is just the platform. On the platform you can put different kind of devices. We also had the experience with the using of the thermal imaging when we look to the tanks according to the different temperature. We are able to recognize if it's the full tank or how is the level of the surface of the liquid inside. Yeah?
Very, very interesting. Thank you so much. 2 quick questions. I think it's for Nelson. Quick question and quick answer, please, because then we will have to wrap up. Can the system also detect biohazards or only chemicals? First question.
Yes, we can. And I'll answer the second question as well in line with that calibration. Yeah. So with TNO, once we get the gases, as I said, all we need to do is put it through a separate with another laser system that we have, and we calibrate the equipment. Yeah, so it's pretty straightforward and easy for us to do. And coming back to one of the first questions, I worked it up and I looked at the SIGIS and HI90 question. So looking at that, so if you look at it, single unified platform, that's OHM. SIGIS and HI90, they're not. Zero consumables. Yep. So all of them are zero consumable. AI and ML Edge, we have it, whereas both of them are limited. Software-driven upgrades, we have it, and they have it all partial. Integrated C2 dashboard, we have it, but the others have it as external. So that's a quick one on that comparison as well between OHM and the other 2 companies that was mentioned.
Perfect. Yes, sir. Thank you very much for this additional answer. I would like to close now. Sorry, so the webinar, and thank very warmly the 3 speakers for their very informative presentation, also providing some very practical experience and situations that I think will repeat in the future. So it gives some good idea what to do in such situation. I think it was very, very instructive, informative. Thank you very much. I would like also to thank Bastien for organizing this webinar, Bastien Kaya, working with me for all the back office. And you will be able to visualize this 5/5 webinar on the YouTube channel of the Direction project, where you can see 4 other webinars that have been recorded on different topics that are of interest for emergency responders. So again, thank you for your participation, for speaking, and I hope it is useful for your private and organization use. Thank you. Bye-bye.
Bye.
Thank you. Bye.
Thank you. Bye-bye.
Thank you. Bye.